This is about the introduction to topics in hypothesis testing. There are areas of inferential statistics: estimation and hypothesis testing. In estimation, we have point estimation and interval estimation. I will show to you a research problem. How effective is the drug in treating male pattern baldness? I have here two specific objectives. First, to estimate the population proportion of patients who will show new hair growth after being treated with drug. Second, to determine whether treatment using the drug is better than the existing treatment that is known to stimulate hair growth among 40% of patients with male pattern baldness. The question: how do we achieve these objectives using inferential statistics? The first objective can be answered by estimation, while the second objective can be answered by hypothesis testing. What is hypothesis testing? Hypothesis testing evaluates a conjecture about some characteristics of the parent population based upon the information contained in the random sample. Usually, the conjecture concerned one of the unknown parameters of the population. Hypothesis is a claim or statement about the population parameter. Example of parameters are population mean and population proportion. The parameter must be identified before analysis. Example: this drug is guaranteed to change cholesterol levels on the average by more than 30%. The mean body temperature for patients admitted to hospital is not equal to 37.0 degrees centigrade. Now, the parameter of interest here is mu, which is the mean body temperature of patients admitted to a hospital. Another example: the proportion of registered voters in a certain municipality favoring candidate A exceeds 0.60 or 60%. The parameter of interest here is P, which is the proportion of registered voters in a certain municipality favoring candidate A. We have to keep in mind, analyze a sample in an attempt to distinguish between results that can easily occur and results that are highly unlikely. We can explain the occurrence of highly unlikely results by saying either that a rare event has indeed occurred, or the things aren't as they are assumed to be. Example to illustrate the basic approach in hypothesis testing. A certain product claims that couples increase their chances of having a boy up to 25%, a girl up to 80%. Suppose we conduct an experiment that includes 100 couples who want to have baby girls, and they all follow the product to have a baby girl. Using common sense, no real formal statistical methods, what should you conclude about the effectiveness of the product if the 100 babies include A. 52 girls, B. 97 girls? First, we normally expect around 50 girls in 100 births. The result of 52 girls is close to 50, so we cannot immediately conclude that the product is effective. In the 100 couples used to special methods of gender selection, the result of 52 girls could easily occur by chance. Taken. The result, 27 girls in 100 births, is unlikely to occur by chance. It could be explained in one of two ways. First, either a rare event has occurred by chance, or the product is effective because of the low probability of getting 97 girls by chance. The more likely explanation is that the product is effective. Further explained, we should conclude that the product is effective only if we get significantly more girls than we would expect under normal or ordinary circumstances. Second, although the outcomes of 52 girls and 97 girls are both above average, the result of 52 girls is not significant, whereas 97 girls does constitute a significant result. We have here the components of formal hypothesis testing. Null hypothesis, this is denoted by its null. This is the statement that is being tested. It represents what the experimenter does to be true, and it contains the condition of equality and must be written in this symbol. Equals, less than, or equal to, or greater than, or equal to. When actually conducting tests, we operate under assumption that the parameter equals some specific values. For the mean, the null hypothesis will be stated in one of these three possible forms. Mu is equal to some value, mu is lesser than some value, and mu is greater than some value. We have to take note that the hypothesized value of mu can be obtained from previous studies or from knowledge of the population. Example of null hypothesis. Null hypothesis corresponding to the common belief that the mean body temperature is 37 degrees centigrade as expressed by its null equals to 37 degrees centigrade. We test the null hypothesis directly in the sense that we assume it is true and reach a conclusion to either reject its null or fail to reject its null. Alternative hypothesis. This is denoted by its a. This is the statement that must be true if the null hypothesis is false. The operational statement of the theory that the experimenter believes to be true and wishes to prove, and is sometimes referred to as the research hypothesis. For the mean, the alternative hypothesis will be stated in only one of these three possible forms. Mu is not equal to some values, mu is greater to some value, mu is lesser to some value. We have to take note that if its a is the opposite of its o, for example, its o is given as mu is equal to 37.0, then it follows that the alternative hypothesis is given by its a, mu not equal to 37.0. Note about using less than or greater than in its null. Even though we sometimes express its null with the symbol greater, lesser or greater, as in mu is greater than 37.0 or mu is lesser than 37.0, we conduct the test by assuming that mu is equal to 37.0 is true. We must have a single fixed value for mu so that we can work with a single distribution having a specific mean. Stating about our own hypothesis. If you are conducting a research study and you want to use a hypothesis test to support your claim, the claim must be stated in such a way that it becomes the alternative hypothesis so it cannot contain the condition of equality. So if you believe that your brand of refrigerator lasts longer than the mean of 14 years, for other brands, state the claim that mu is greater than 14, where mu is the mean life of your refrigerator. So your its null is mu equals 14 versus your its a mu greater than 14. In this context of trying to support goal of the research, the alternative hypothesis is sometimes referred to as research hypothesis. Also, in this context, the null hypothesis is assumed true for the purpose of conducting the hypothesis test, but it is hoped that the conclusion will be rejection of the null hypothesis so that the research hypothesis is supported. Example of a research problem. Suppose that the government is deciding whether or not to approve the manufacturing of new drug. A drug is to be tested to find out if it can reduce blood sugar level. The Bureau of Food and Drug will not allow the marketing of the drug unless there is strong evidence that it is effective. A random sample of 98 middle-aged men has been selected for the experiment. Each man is given a standard daily dosage of the drug for 2 consecutive weeks. Their blood sugar levels are measured at the beginning and at the end of the test. The interest is to determine if the intake of the drug lead to reduced sugar levels. That is, a hypothesis test will have to be performed to determine if the drug is effective or not. Based on the results of the experiment, the director of the BFOD will decide whether to release the drug to the public or postpone its release and request for more research. To perform a statistical hypothesis test, we must firstly identify the parameter of interest and have some educated guess about the true value of the parameter. In the case of the BFOD example, the possible states of the drug effectiveness are referred to as hypotheses. Because the director wants to know whether it is effective or not, either of the following hypothesis applies. The drug is ineffective or the drug is effective. Measure the effectiveness of the drug for its middle-aged man. We can look at the percent change in blood sugar levels experienced by all middle-aged men who took the drug before and after they took the drug. We summarize the effectiveness in terms of the population mean. Let mu be the population mean of the percent chance in sugar levels. BFOD decide to classify the drug as effective only if, on the average, it reduces the blood sugar levels by more than 30%. So mu is greater than 30%. So stating the null hypothesis that represent no practical change in cholesterol levels before and after the drug use, in terms of mu, we say mu is less than 30%. For alternative hypothesis, mu is greater than 30%. Mu is lesser or equal to 30%. Stating the alternative hypothesis, mu is greater than 30%. So whenever sample results fail to support the null hypothesis, the conclusion we accept is the alternative hypothesis. In our illustration, if results from the sample of percentage change in blood sugar levels fail to support its null, then the director concludes it's a and says that the drug is effective. What is a test of significance? A test of significance is a problem of deciding between null and the alternative hypothesis on the basis of the information contained in a random sample. The goal will be to reject its null in favor of its path because the alternative is the hypothesis that the researcher believes to be true. If we are successful in rejecting its null, we then declare the result to be significant. Note about testing the validity of someone else's claim. Sometimes, we test the validity of someone else's claim, such as the claim of a bottling company that the mean amount of soft drink in cans is at least 355 ml, which becomes the null hypothesis of mu greater or equal to 355 355 ml. In this context of testing the validity of someone else's claim, their original claim sometimes becomes the null hypothesis because it contains equality. And it sometimes becomes the alternative hypothesis because it does not contain the equality. So this means that null hypothesis contains equality, while alternative hypothesis does not contain equality. Let's have the two types of errors, type 1 error and type 2 error. Type 1 error, mistake or the error of rejecting the null hypothesis when it is true. It is not a miscalculation or procedural mistake. It is an actual error that can occur when a rare event happens by chance. The probability of rejecting the null hypothesis when it is true is called the significance level, alpha. The value of alpha is typically predetermined, and very common choices are alpha is equal to 0.05 and or 0.01. Example of type 1 error. The mistake of rejecting the null hypothesis that the mean body temperature is 37.0 when the mean is really 37.0. Or the BFAD allows the release of an ineffective medicine. Type 2 error, when the mistake of failing to reject the null hypothesis when it is false, and the symbol B, beta, is used to represent the probability of type 2 error. Example, mistake of failing to reject the null hypothesis, mu is equal to 37.0 when it's actually false, that is, the mean is not 37.0. Or the BFAD does not allow the release of an effective trap. So this is the summary for possible decision in hypothesis testing. The decision here, side, and the true situation here in this side. If we decide to reject the null hypothesis, when the null hypothesis is true, then we are committing type 1 error, that is rejecting a true null hypothesis. If the decision is rejecting the null hypothesis when it is false, then the decision is correct. When we fail to reject the null hypothesis when the hypothesis is true, then we got a correct decision. But if we fail to reject the null hypothesis when it is false, then we are committing type 2 error, that is failing to reject a false null hypothesis. This is the analogy of decisions and hypothesis testing. So this is about the trial. We have here the verdict as innocent and guilty, while here the truth. If the verdict is innocent and is really innocent, the truth is innocent, then we are correct in our decision. But if the verdict is innocent and the truth is guilty, then an error is committed. While if the verdict is guilty and the truth is innocent, then we are committing an error. While when the truth is guilty and the verdict is guilty, then the decision is correct. Controlling type 1 and type 2 errors. The experimenter is free to determine alpha. So, if the test leads to the rejection of its null, the researcher can then conclude that there is sufficient evidence supporting its A at alpha level of significance. Usually, B or beta is unknown because it's hard to calculate it. The common solution to this difficulty is to withhold judgment if the test leads to the failure to reject its null. Alpha and beta are inversely related. For a fixed sample size n, as alpha decreases, beta increases. In almost all statistical tests, both alpha and beta can be reduced by increasing the sample size. Because of the inverse relationship of alpha and beta, setting a very small alpha should also be avoided if the researcher cannot afford a very large risk of committing a type 2 error. The choice of alpha usually depends on the consequences associated with making a type 1 error. We have here the common choices of alpha, 0.01 or smaller. The consequences of type 1 error is very serious. 0.05, moderately serious. 0.10, not so serious. Usual practice in research and industry is to determine in advance the values of alpha and the samples. And so the value of beta is determined. Depending on the seriousness of the type 1 error, try to use the largest alpha that we can tolerate. For type 1 errors with more serious consequences, select smaller values of alpha. Then choose a sample size n as large as is reasonable, based on consideration of time, cost, and other such relevant factors. Illustrate type 1 and type 2 errors. Consider here a certain brand of chocolate and a brand of aspirin tablets. The chocolate packets contain 1,498 candies. The mean weight of the individual candies should be at least 0.9085 grams because the chocolate package is labeled as containing 1,361 grams. The aspirin package is labeled as holding 30 tablets, each of which contain 325 milligrams of aspirin. Because chocolates are candies used for enjoyment, whereas aspirin tablets are drugs used for treatment of health problems, we are dealing with two very different levels of seriousness. If the chocolates don't have a population mean weight of 0.9085 grams, the consequences are not very serious. But if the aspirin tablets don't have a mean of 325 milligrams of aspirin, the consequences could be very serious. If the chocolate have a mean that is too large, the company will lose some money, but consumers will not complain. In contrast, if the aspirin tablets have too much aspirin, the company producing it would be faced with consumer lawsuits. Consequently, in testing the claim mu is equal to 0.9085 grams for chocolate, we might choose alpha equals to 0.05 and a sample size of 100. N is equal to 100. In testing the claim of mu is equal to 325 milligrams for aspirin tablets, we might choose alpha of 0.01 and a sample size of n equals to 500. The smaller significance level alpha and a large sample size n are chosen because of the more serious consequences associated with commercial drugs. Test statistics. Statistics computed from the sample data that is especially sensitive to the differences between its null and its A. The test statistics should tend to take on certain values when its O is true and different values when its A is true. The decision to reject its O depends on the value of test statistics. A decision roll based on the value of the test statistics. Reject its null if the computed value of the test statistics falls in the rejection region. Region of rejection or critical region. The set of all values of the test statistics will lead to the rejection of its null. These are the factors that determine the rejection region. The behavior of the test statistics if the null hypothesis were true. The alternative hypothesis, the location of the region of rejection depends on the form of its A. Level of significance. The smaller alpha is, the smaller the rejection region. The values or values that separate the critical region from the values of the test statistics that would not lead to rejection of the null hypothesis. It depends on the nature of the null hypothesis, the relevant sampling distribution, and the level of significance. Types of tests. We have tail test, left tail test, and right tail tests. Two-tailed test, if we are primarily concerned with deciding whether the true value of a population parameter is different from a specified value, then the test should be two-tailed. For in this case, the mean we say it's a mu is not equal to mu. Left-tailed tests. If we are primarily concerned with deciding whether the true value of a parameter is less than a specified value, then the test should be left-tailed. For the case of proportion, we say P is less than a certain value of P. Right-tailed tests. If we are primarily concerned with deciding whether the true value of a parameter is greater than a specified value, then we use right-tailed tests. For the case of the standard deviation, we say standard deviation is greater than a certain value of the standard deviation. This is an illustration of level of significance and the rejection region. The shaded portion of the curve is the rejection region for left-tailed or right-tailed or for two-tailed tests, while the unshaded portion is the non-rejection region. P-value, the smallest level of significance at which hypothesis null will be rejected based on the information contained in the sample. So this is an alternative form of decision rule. This is based on the p-value. Reject its null if the p-value is less than or equal to the level of significance alpha. Example of making decision using the p-value. If the level of significance is alpha 0.05, the p-value is 0.01, reject its O. That is the decision. If it is 0.05, again, the decision is to reject its O. But if the p-value is 0.10, so this is now larger than 0.05, then we will not reject its null. Conclusion and hypothesis testing. First, fail to reject the null hypothesis. Second, reject the null hypothesis. Some texts say, accept the null hypothesis instead of fail to reject the null hypothesis. So whether we use the term accept or fail to reject, we should recognize that we are not proving the null hypothesis. We are merely saying that the sample evidence is not strong enough to warrant rejection of the null hypothesis. So this is an example wording of final conclusion. To start, we have to question, does the original claim contain the condition of inequality? If the answer is no, the original claim does not contain equality and becomes its so do not reject the null hypothesis. If it is yes, then reject null hypothesis. If it is no, then fail to reject null hypothesis. We can state our final conclusion as the sample data support the claim that the original claim will follow. We know we can state this as our final conclusion. The sample does not provide sufficient evidence to support the claim that, so you add the original claim. Example in making final decision. If you want to justify the claim that the mean body temperature is different from 37.0 degrees centigrade, then make the claim that mu is not equal to 37.0. This claim will be an alternative hypothesis that will be supported if you reject the null hypothesis of mu is equal to 37.0. If on the other hand you claim that the mean body temperature is 37.0 degrees centigrade, that is mu is equal to 37, you will either reject or fail to reject the claim. In either case, you will not support the original claim. Let us have summary of the steps in hypothesis testing. First of all, we need to determine the objectives of the experiment. And this is the responsibility of the researcher. First step, state the null and alternative hypothesis. Second, decide on a level of significance, that is the alpha. So, determine the testing procedure and the methods of analysis. This is now the responsibility of the statistician. Third, decide the type of data to be collected and choose an appropriate test statistics and testing procedure. Next, we have state the decision rule. Then, collect the data and compute for the value of the test statistics using the sample data. Number 6, if the decision rule is based on region of rejection, check if the test statistics falls in the region of rejection. If yes, reject, it's not. If decision rule is based on p-value, determine the p-value. If the p-value is less than or equal to alpha, reject, it's null. Then, the last, interpret the result. Thanks for viewing and subscribing.